In this video, we will be looking at two of Java's standard library collection classes, HashSet and HashMap, and some of the situations in which you might like to use these in preference to classes like ArrayList and LinkedList. In the examples, we will be coding using the BlueJ IDE, but the principles are independent of the IDE. The ArrayList and LinkedList classes in the java.util package are probably familiar to you already, as they are among the most commonly used flexible-sized collection classes in Java. While they are great for storing multiple objects without having to know in advance how many you wish to store, they have one major disadvantage over HashSet and HashMap. There is no direct way to relate a particular object to its location in the collection. In other words, knowing where an object is in an array list or linked list requires that either you already know its numerical position or you have to search for it, and searching can be a relatively costly operation if the collection is large. In contrast, the hashed collections provide fast, direct access to an object within them. To illustrate some of the differences between ArrayList and HashSet, let's work with a program that performs simple textual analysis. For instance, you might want to try to work out whether two documents were authored by the same person by analyzing the vocabulary used in both and relative word frequencies. For this task, we will need a dictionary, and we will want to look words up in the dictionary. Our program will use one with about 65,000 words in it, so we will want the looking up process to be efficient. We won't build a full application, but we'll just limit ourselves to counting word occurrences and identifying words that are not in the dictionary as a characteristic of a particular writer. The program will contain a few features that you might not be fully familiar with, such as file reading, but that should not make the aspects related to the collections difficult to understand. Here is our starting point. Don't be intimidated by the number of classes in the diagram. Essentially, the program consists of three alternative implementations of a dictionary: unordered word list, ordered word list, and word set. Both unordered word list and ordered word list use an array list to store the words. The difference between them is that one stores the words in an arbitrary order and the other stores them sorted alphabetically. The word set class stores the words in a hash set, which imposes no particular order on them. The three arrows leading to dictionary essentially just mean that the three classes all have similar methods. Those methods are contains to look up a word and size to return the number of words in the dictionary. We have done things in this way to simplify some of the code in the dictionary demo class, as it means that we don't have to write three different versions of the code to work with each dictionary class. In terms of understanding how they work, the three dictionary classes can be treated as ordinary Java classes. Here is the code for the unordered word list class. The constructor reads words from the dictionary file and stores them in its array list. We will not make any assumption about the order of the words in the list and treat it as having a random ordering. The class defines the two methods common to all the dictionary classes, contains and size. Both simply call the equivalent methods of the array list. It is important to appreciate that the contains method of ArrayList performs a linear search through its elements from beginning to end. It has no special features that allow it to find an element any more quickly than that. It follows that it will take the contains method a relatively long time to determine if something is not in the list, and the time taken for a search is directly proportional to the length of the list. The ordered word list class is similar to the unordered one, but has two main differences in the constructor and the contains method. The constructor arranges for the list to be sorted after it has been filled, and this is an essential condition for the implementation of the contains method. The contains method can now use a different way to find if a word is in the list. It calls the binary search method of the collections class. For details of how this works, you can check its description in the Java API. Its essential feature is to take advantage of the fact that the list is sorted. As illustrated here with a sorted list of letters, rather than starting at the beginning of the list and working linearly through it, it starts in the middle and works out whether what is being searched for comes earlier or later in the order than the middle one. If it comes earlier, then the search can completely ignore all of the elements in the second half of the list, effectively reducing the size of the list by half. It can then repeat that same process with the remaining half of the list, and again reduce the number of elements to search by half. At each comparison, half of the remaining elements are eliminated. This means that relatively few elements in the list need to be examined in total to find the one being searched for, or to conclude that it is not in the list. This means that using this technique to search a sorted list is very much faster than searching an unsorted one, as we shall see. The final dictionary class, WordSet, is very similar to the unordered class with the single exception that it uses a hash set rather than an array list to store the words. However, the big difference we shall see is that the HashSets contains method is significantly faster than the array lists because, unlike an array list, a hash set does have a way of directly relating the objects it contains to their locations within its internal storage. Let's take a look at the differences in lookup times between the three classes. The dictionary demo class allows us to look up either only words that are known to be in the dictionary or an equal mix of words that are in or not in. Let's see the different lookup times for each class by calling lookup known. We will be searching for 6,500 words that are definitely in the dictionary. That's about 10% of the total number of words. These are selected randomly from the dictionary, so they will be distributed fairly evenly throughout the collections. The output shows that searching the sorted list is about 100 times faster than searching the unsorted list. Let's try searching for a similar number of words, but with only half of those being definitely in the dictionary. The search time for the unsorted list is now about 1.5 times that for when all the words are known. That makes sense because each search to find a known word will require on average about half the list to be searched, but each search for an unknown word will require the whole list to be searched every time. In contrast, there is no significant difference in the time to search the sorted list because relatively few comparisons are needed to determine whether an unknown word is in the place it would occupy. Similarly, the set can tell almost immediately if an element is present or not. Although the sorted list and the hash set have similar lookup times, the sorted version can only be used if it's possible to keep the data in the list sorted, which will not always be practical. How does a hash set manage to directly associate an object with the position it occupies within the set's internal storage? In this video we won't cover the full details of hashing, but you should be able to understand the basic idea from a simple example. Just like an array list, a hash set uses an internal fixed-size data structure called an array to store its elements. The elements of an array are always accessed by integer indices 0, 1, 2, and so on. In essence, the hash set takes each object it has to store and uses the object's contents to create an integer value that is then used as the index into the hash set's array where that particular object is to be stored. The process used to create the integer value is called a hash function, and Java allows you to define how the contents of an object are converted to a hash value. For instance, a possible approach for the string class would be to assign a unique numerical value to each letter of the alphabet, 1 for A, 2 for B, and so on. Then a hash for a word could be formed by adding up the values of the letters and using the resultant sum as the index for that word. Converting the letters to numbers and forming the sum would be the hash function. Now you can probably immediately spot some problems with this very simple approach. A few might be, what about all the other characters that aren't lowercase letters? Because not all strings will be lowercase words. What about words that have the same letters but in a different order? Top and pot, for instance. Simply adding up the letter values would give the same hash value for two different words and require that different words be stored at the same index, which is not what we want. This is called a collision. What if the hash value is an integer that is larger than the number of elements in the data structure's internal array? In practice, these problems can be solved quite easily, and we won't go into details here. If you are interested in the details, just do a search for hashing or hash function. The important thing is the principle. With a suitable hash function, it is possible to turn the data in any object into a positive numerical value that can be used as the index for where to store that object in the array. As long as that conversion process is relatively efficient and collisions can largely be avoided, hashing provides a very fast way to directly associate an object with where it is stored in a data structure like a hash set. That is why lookup is so fast in our dictionary example. Let's now use what we have learned from this example in a further project which adds some elements of textual analysis. We only need one of the dictionary implementations, so we will go with the set-based one as it is the most efficient for lookups. This extension will introduce another hash-based Java collection, the HashMap. HashMap uses exactly the same technique as HashSet for storage. For an analysis of word usage, there are lots of different things we could look at. For instance, vocabulary size, relative frequency of use of particular words compared to others, usage of unusual words, word combinations such as pairs of words used together, these are called n-grams, and so on. We won't cover all of these, but you might like to have a go at completing the list as follow-up exercises and maybe adding other ideas of your own. If we are going to count word usage, then we clearly need to be able to associate each word with how many times it is used in the text. In other words, we want to create word-integer pairings. The type of data structure to use is called a map, because we want to map words to integers. That sounds a bit like what hashing does, but in this case the integers are not going to be calculated from the text of the word. Rather, the integer is the count of each word's occurrences, and this will vary as we read through the text and find new occurrences. The way we will calculate the usage counts is to read each word in the text, look up its current count in the map, and replace it with a value 1 greater. Clearly we are going to be doing a lot of lookup of words. The text we are using here has over 120,000 words, so we will want lookup to be efficient. That means we want our word count data structure to use hashing. The HashMap class from the java.util package is ideal for this. It is a map data type that uses hashing, just like a HashSet is a set data type that uses hashing. Notice that the class names have been chosen to reveal details of their implementation, just like ArrayList reveals that it is a list implemented with an array. The dictionary demo class defines instance fields for the dictionary and word count map. Notice that because a HashMap is associating each word with its count, we need to declare a HashMap variable with the type of each, a string and an integer. The first type is called the key type and the second type is called the value type. Each word will be a key into the map and each count will be the key's associated value. This has two consequences. When we store a word in the HashMap, we will also be storing a count to go with it. In other words, we will always be putting a key-value pair into the HashMap. The method for doing this is called put, and it takes one parameter for the key and another for the value. Whenever we look something up in the HashMap, we have to pass in the relevant key to its get method, which then returns the associated value. In this program, we will pass in a string, and the get method will return an integer. If a particular word has not yet been added to the HashMap, then the get method will return null to indicate that there is currently no count. We see both get and put in action in the read text method. The read text method checks that the file to be analyzed exists and then uses a scanner to read it word by word. The core part for our understanding of how the HashMap is used to record the counts is these lines. The word is passed to the get method as the lookup key. If this is the first time the word has been encountered in the text, then it won't exist as a key in the HashMap and null will be returned as the associated value. On the other hand, if it has already been seen, a non-zero count will be returned. We check for null and set the count to 0 in that case. Finally, the HashMap's put method is used to associate the updated count with the word key. HashMap actually has extended versions of the get and put methods called get or default and put if absent, but we won't cover those here. You can look up how they work in the API documentation. Once the text has been read and the word counts found, we see that we can do things like finding the most commonly used word. For the sake of simplicity, we don't attempt to find more than one with the highest count. This illustrates that the typical way to iterate over a HashMap is to iterate over its keys using a for each loop. Note too that since we are only using known keys with the get method, we don't have to check for null this time because we know there will always be a count associated with each word. Another thing we can do is to look for which words in the text are not in the dictionary. That could be used to reveal unusual words the author has used as a clue to identifying them, but it could also be useful in helping us to extend the dictionary with new words. We won't take this example any further, but there are plenty of ways in which you could add extra features for further practice. For instance, you might want to have a set of very common words that you are not interested in counting, words like he, she, the, and so on. You could store those in a set and avoid counting them while reading the text, or remove them from the HashMap after all words have been counted. Why not try those as exercises? In this video, we have looked at HashSet and HashMap from the java.util package as complementary data structures to ArrayList and LinkedList. Both HashSet and HashMap use the principles of hash functions to provide direct access to the data they store. HashSet stores individual objects, while HashMap stores key-value pairs. When you write a class, you actually have the option to define a hash function for its data, and you can learn more about this by researching the hashcode method of the object class.